Okay, now we are going to learn about capacitor with dielectric. So let's look at parallel plate capacitor with air gap first. So we have a figure here which shows two parallel plate capacitor with equal area A, and the plates are separated by distance D, and the space between the plates is vacuum. When this capacitor is charged, plates will have charges of equal magnitude but opposite signs. So this will have positive Q and the other plate will have negative Q. Then there will be a potential difference V across the plate. The capacitance of air-filled parallel plate capacitor can be written in the form of C0 is equal to epsilon naught A over D, in which C0 is the capacitance of capacitor with air gap, epsilon naught is the permittivity of free space, which is a constant value, D is the distance between the two plates, and A is the area of each plate. And if you look back at the equation, you can see that C0 is directly proportional to the area of the plate. So if the area of the plate increase, then the capacitance will also increase. And then we also can see that C0 is inversely proportional to the distance between the plates. So if the distance between the plates is increased, then C0 will decrease. Okay, let's define dielectrics. A non-conducting or insulating material which is placed between the plates of a capacitor. When a dielectric, such as rubber, glass or wax paper, is inserted between the plates of a capacitor, the capacitance increases by a factor of epsilon R or K, which is called the dielectric constant or relative permittivity of the material. So if you want to find the capacitance for a capacitor with dielectric, you can use the formula C is equal to epsilon A over D. C is the capacitance of capacitor with dielectric, epsilon is the permittivity of dielectric material, D is the distance between the two plates, and A is the area of each plate. Please take note of the difference between C and also the C0. So this one is for capacitor with dielectric, and then C0 is for capacitor with air gap. So what is dielectric constant, which is epsilon R or K, or another name for it is relative permittivity? It is the ratio between the capacitance of a given capacitor with space between plates filled with dielectric C, and the capacitance of the same capacitor with plates in a vacuum. There is no unit for dielectric constant. Basically, from the definition, you know that epsilon R is the ratio between C and C0. So you will get this equation. And another way to express dielectric constant is epsilon R is equal to epsilon over epsilon naught equal to V0 over V and equal to E0 over E. So V0 here is the potential difference of capacitor with air gap, and V is the potential difference of capacitor with dielectric, and E0 is the electric field strength of capacitor with air gap, and E is the electric field strength of a capacitor with dielectric. Look at example 7. You have a vacuum parallel plate capacitor which has an area of 150 cm square, and separation D is equal to 2 mm. The capacitor is then charged to a potential difference of V0 equals to 2000 volt. And then the battery is disconnected and a dielectric sheet of the same area A will be placed in between the plates as shown in this figure. So initially there is no dielectric between the plate, just air gap, and then we place a dielectric between the plates. So in the presence of the dielectric, the potential difference will be reduced to 500 volt. So we have a new voltage which is 500 volt. So this one is before inserting dielectric, and this is after. So the question are asking you to find initial capacitance of capacitor, the charge on each plate before the dielectric is inserted, the capacitance after the dielectric is in place, the relative permittivity, the permittivity of dielectric material, the initial electric field, and also the electric field after the dielectric is inserted. We have A is equal to 150 centimeter square, which is converted into meter square, and then D is 2 millimeter, V0 is 2000 volt, V is 500 volt. So question A asks you to find the initial capacitance of the capacitor. So it's asking you to find the capacitance of capacitor with air gap. That is C0. To find C0, you have to use epsilon naught A over D. Epsilon naught is a constant. The value is 8.85 times 10 to the power of negative 12. And then the area is given 150 times 10 to the power of negative 4. And then the separation between the plate is also given, which is 2 millimeters, so 2 times 10 to the power of negative 3. And then you will get the initial capacitance to be 6.64 times 10 to the power of negative 11 farad. Question B wants you to find the charge on each plate before the dielectric is inserted. So once again, this is the charge for capacitor with air gap. So you want to find Q0 because you haven't inserted the dielectric yet. So Q0 is equal to C0 V0, and C0 you have calculated to be 6.64 times 10 to the power of negative 11, and V0 is given, which is 2000 volt, and you will get Q0 is equal to 1.33 times 10 to the power of negative 7 coulomb. Question C wants you to find the capacitance after dielectric is placed. So this is capital C. So initially, before dielectric is inserted, we have Q0 is equal to 1.33 times 10 to the power of negative 7 coulomb. And then we disconnect the battery and insert the dielectric. So even in the presence of dielectric, the charge Q on each plate will be the same as before the dielectric was inserted, which means that Q will also be equal 1.33 times 10 to the power of negative 7 coulomb. So we want to find C, and we can immediately use the formula C is equal to QV. So Q is 1.33 times 10 to the power of negative 7, and V is 500. So you will get C is equal to 2.66 times 10 to the power of negative 10 farad. And then question D wants you to find the relative permittivity. So relative permittivity is also known as the dielectric constant, which is epsilon R. So you want to find epsilon R. There are a few formulas for epsilon R, but based on the information that we have, we can use epsilon R is equal to C over C0, and C is 2.66 times 10 to the power of negative 10 divided by the initial capacitance, which is 6.64 4 times 10 to the power of negative 11, and you will get epsilon r to be equal 4.01. So question E wants you to find the permittivity of dielectric material. So permittivity of dielectric material is epsilon. So to find epsilon, you can use the formula epsilon r is equal to epsilon over epsilon naught, because you already have calculated epsilon r. So you can substitute in 4.01 and then equal to epsilon. Epsilon naught is a constant, which is 8.85 times 10 to the power of negative 12. And then calculate this to get epsilon is equal to 3.55 times 10 to the power of negative 11 coulomb square per Newton per meter square. Question F asks you to find the initial electric field, which is E naught. So to solve for this question, you have to recall back concept from chapter 1, which is electrostatic, in which the electric field is equal to the potential difference divided by the separation between the two plates. So you will get E naught is equal to V naught over D. Substitute in the value of V naught, which is 2000 volt. Separation is 2 millimeter, so 2 times 10 to the power of negative 3, and you will get E naught is equal to 1 times 10 to the power of 6 volt per meter. And then for question G, it wants you to find the electric field after the dielectric is inserted, which is E. So to find E, there is two methods. So you can use epsilon r is equal to E naught over E, or you can use the same formula from chapter 1. So you will get E is equal to V over D. So if I use E is equal to V over D, then I just substitute in the value of potential difference after dielectric is inserted, which is 500 volt, divided by 2 times 10 to the power of negative 3. And I will get the new electric field to be 2.49 times 10 to the power of 5 volt per meter. Okay, moving on to the final agenda for this chapter, we are going to describe the effect of dielectric on a parallel plate capacitor. So consider a parallel plate capacitor as shown in this figure. Initially, the plates are separated by a vacuum, and it is connected to a battery. So once it is connected to a battery, you have charge on the plates, positive Q and negative Q. Okay, and then the battery is now removed, and the charge will remain constant. The electric field between the plates is uniform and has a magnitude of E naught. Meanwhile, the separation between the plate is D. When a dielectric is placed between the plates, so this is the dielectric placed between the plates, the molecules of the dielectric tend to become oriented with their positive ends pointing towards the negatively charged plate, and then the negative end will be pointing towards the positively charged plate. From here, the result is a build-up of positive charge on one surface of the dielectric and of negative charge on the other. From the figure, the number of field lines within the dielectric is reduced. Thus, the applied electric field E naught is partially cancelled. Because the new electric field strength E is less than E naught, then the potential difference V across the plate will be less as well. And to find the potential difference across the plate, you have to use V is equal to ED. And since V is smaller, while Q remains the same, then capacitance will be increased by the dielectric, because we know that C is equal to Q over V if Q is constant, then if V decreases, C will increase. So as a result of inserting dielectric between the plates, we have higher capacitance. We have reached the end of the chapter. Next chapter you will learn chapter 3, which is on electric current and direct current circuits.